Tonight, we are going to follow Voyager 1 farther into the future than any mission was ever designed to survive. Long after its last instrument falls silent, the spacecraft will keep moving through interstellar space. It will pass beyond the sun's distant cloud of comets, drift near unfamiliar stars, and continue around the Milky Way, while the solar system slowly becomes unrecognizable. Billions of years from now, the sun will swell into a red giant. The inner planets may be destroyed, and the world that launched Voyager may no longer exist. Yet somewhere in the galaxy, a small machine carrying the sounds and images of Earth may still be traveling. So tonight, the question is simple. Where will Voyager 1 be when the sun finally dies? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could add one final sound from Earth to Voyager's golden record, what would it be? Let me know in the comments. I will pin the most creative answer. Tonight, you are watching the Just About Space channel, talking about where Voyager 1 will be when the sun dies. Voyager 1 was never meant to become a witness to deep time. It was built for a much shorter journey, one shaped around the giant planets, and a rare alignment that allowed a spacecraft to move from Jupiter towards Saturn. Its original mission belonged to the late 20th century, when the outer solar system was still known mainly as distant points of light. The spacecraft was expected to pass those worlds, return its images and measurements, and eventually fade into silence. Instead, it kept going. The cameras that once revealed Jupiter's storms and Saturn's rings are no longer taking pictures. Most of the instruments that defined the planetary mission have been silent for decades. Yet, the spacecraft itself continues to function far beyond the region it was designed to explore, carrying a small amount of electrical power through a place no earlier machine had ever reached. Nearly half a century after launch, Voyager 1 is still sending information home. That fact can sound simple until the distance is considered. The spacecraft is now so far from Earth that a radio signal needs almost an entire day to cross the space between them. A command sent from the ground cannot produce an immediate response. It travels outward for many hours, reaches a machine moving through interstellar space, and any answer must then make the same journey back. A single exchange stretches across nearly 2 days. The spacecraft does not know that this is remarkable. It follows instructions, measures its surroundings, protects its orientation, and sends a signal too weak for any ordinary receiver to notice. On Earth, enormous antennas listen for it through the background noise of the sky. What arrives is not a voice. It is a narrow stream of data from a machine launched in 1977. The technology on board belongs to another era. Its computers hold only a tiny fraction of the memory found in a modern phone. Commands are carefully prepared because there is no quick way to correct a mistake. Some of the engineers who designed the spacecraft are no longer alive, and the people operating it today often work with records created before many of them were born. Voyager has outlived the world that built it, in a very literal sense. The cities beneath its launch path have changed. The computers used to plan the mission have become museum objects. Entire generations have grown up after the spacecraft left Earth. Yet somewhere beyond the protective influence of the solar wind, the same machine continues following a path written into its motion almost 50 years ago. Its survival was not expected to last this long, but it was not accidental either. Voyager was built with redundancy because no repair crew could follow it. Important functions had backups. Systems were designed to tolerate radiation, cold, and years of operation. The spacecraft could switch between components when one failed. Engineers could rewrite procedures, alter how the hardware was used, and find new ways to preserve power. But redundancy is not immortality. Every backup that becomes necessary removes another layer of protection. Every component switched off makes the spacecraft slightly simpler and more fragile. Voyager survives because enough of its essential systems still work together, not because time has left it untouched. The machine has been aging since the moment it launched. Its power source reveals this most clearly. Voyager does not use solar panels. At its present distance, sunlight is far too weak to support the mission. Instead, the spacecraft carries radioisotope power systems that convert heat from the natural decay of plutonium into electricity. The process has no moving parts, which helped make it reliable for an extraordinarily long time. But the heat slowly declines, and the equipment that converts that heat into electricity also becomes less efficient. Year by year, the spacecraft has less power available. The loss is gradual, measured in only a few watts annually. A few watts do not sound important on Earth. A small light uses more. But on Voyager, every watt has to be assigned carefully. It may keep an instrument operating, warm a fuel line, power a computer, maintain communication, or control the spacecraft's orientation. There is no new energy coming. The mission continues by deciding what it can live without. Over the years, heaters have been turned off. Instruments that completed their work were shut down. Systems once considered necessary were operated at temperatures far below their original design limits. Each decision preserved power for the remaining science and for the basic functions that keep the spacecraft alive. This creates an unusual kind of mission planning. The Voyager team is no longer choosing only what to study. It is choosing which parts of the spacecraft will remain awake. In April 2026, another science instrument on Voyager 1 was switched off to conserve power. The spacecraft was left with two operating scientific instruments, one measuring magnetic fields and another listening to plasma waves in the space between stars. They do not produce the colorful images associated with the early mission. Their work is quieter. They measure an environment that cannot be seen, recording changes in fields and particles far beyond the heliopause, where the influence of the solar wind gives way to interstellar space. Every reading comes from a region no functioning spacecraft had entered before Voyager. The data are valuable partly because the opportunity may never be repeated in the same way. Other probes will eventually travel outward, but they may follow different directions, carry different instruments, or reach the same distance in another century. Voyager 1 is measuring this path now, with hardware built before the first space shuttle launch. It is old enough that every successful transmission feels borrowed from the future. The engineers do not know exactly how long the remaining instruments will continue. Careful power management may allow scientific measurements to continue into the 2030s, but that is not a promise. A single unexpected failure could shorten the mission. A component that has survived for decades may stop without warning. There is no way to replace it. This uncertainty follows every contact with the spacecraft. Mission Control sends commands knowing that the reply will come much later. When the signal returns, it confirms not only that the instruction worked, but that Voyager remained alive during the silence. The waiting has become part of the mission. For most spacecraft near Earth, silence lasting many hours would suggest a serious problem. For Voyager, it is normal. The distance requires patience. The operators work with a machine that is always describing the past, because every bit of information began its journey many hours before it reached Earth. By the time the data are received, Voyager is already farther away. Small thrusters keep the antenna pointed toward Earth. That alignment is essential. The radio beam is narrow, and the spacecraft must maintain enough control to direct it across billions of kilometers toward a moving planet that cannot be seen as a large target. If Voyager loses the ability to point correctly, the mission may end even if the transmitter and instruments still work. The spacecraft could continue producing data that no one receives. This risk became painfully clear when Voyager 1 stopped returning understandable engineering and science information in late 2023. The radio signal was still present, showing that the spacecraft had not disappeared, but the data inside it had become unusable. For months, engineers worked across the enormous delay to understand a computer problem in hardware that could not be touched. They eventually traced the failure to a damaged portion of memory and reorganized the spacecraft's software so that the necessary code could be stored elsewhere. In 2024, usable engineering and scientific data returned. The recovery did not make Voyager younger. It showed how much knowledge and patience could still be used to keep it alive. A repair on Earth often means replacing a broken object. A repair on Voyager means changing how the remaining pieces work together. Engineers cannot open a panel or install a new computer. They can only send instructions through the dark and ask the spacecraft to rearrange itself. The machine has become partly defined by these adaptations. It no longer operates exactly as it did at launch. Parts have failed, others have been repurposed. Old systems have been asked to perform new roles. Procedures have changed as power declined and knowledge of the aging spacecraft improved. Voyager survives not by remaining unchanged, but by becoming a simpler version of itself. The same process will continue. More instruments will eventually be shut down. More heaters may be sacrificed. Communication may become less reliable as the electrical supply falls and the spacecraft moves farther away. The Deep Space Network can listen with extraordinary sensitivity, but the signal cannot remain detectable forever. Voyager transmits with power comparable to a small household light, and that energy spreads across space before a tiny fraction reaches Earth. The antennas listen for something almost unimaginably faint. The spacecraft does not need to become much weaker before the connection becomes difficult. A small drop in available transmitter power, a problem with the antenna, or the loss of stable orientation could place the signal below what Earth can recover. There may be no single moment when everyone knows the final message has arrived. A transmission could be interrupted. The team might continue listening. Another weak signal could appear. Commands might be sent for weeks or months in the hope that Voyager can respond. The end may be recognized only after enough silence has passed. This is different from the dramatic ending often imagined for a spacecraft. Voyager is unlikely to explode in a distant flash or fall suddenly into a planet. Its active life will probably narrow slowly. One instrument stops, then another. Engineering information becomes less complete. Contacts become more difficult. Eventually, Earth hears nothing. Yet even then, the spacecraft will not be dead in the same way a machine on the ground becomes dead. It will still possess a shape, a trajectory, and a history. Its computers may be silent, but its body will continue moving through the galaxy. The end of the mission is not the end of the journey. That difference is what makes Voyager unique. That silence is approaching, one careful decision at a time. Each instrument turned off extends the life of the others. Each watt saved delays the moment when the radio becomes too weak. Every successful command pushes the active mission slightly farther into the future. But no strategy can prevent the final decline. The power source will continue fading, the hardware will continue aging. The distance will continue growing. At some point, the last operating instrument will stop collecting data. Perhaps engineering information will continue for a while after that. Perhaps the spacecraft will still answer simple commands even when no science remains. Then the answer will weaken. One day, Earth will send a command and receive nothing useful in return. The people listening may not immediately know whether the silence is temporary. They will search, repeat, adjust, and wait through the long communication delay. But eventually, the uncertainty will end. Voyager 1 will have sent its final signal. And when Earth can no longer hear the machine that refused to end, Voyager's far longer journey will finally begin in complete silence. The final signal will probably not feel final when it arrives. It may look like another weak transmission, another narrow stream of engineering data crossing the noise between the stars. The antennas on Earth will receive it, process it, compare it with earlier messages, and continue listening for the next one. No warning light will appear in the sky. No voice will announce that the connection has ended. Voyager will simply fail to answer. At first, that silence may be treated as a problem to solve. Engineers may send commands, adjust frequencies, search for the carrier signal, and wait through the long delay for a response. The spacecraft has recovered from serious failures before, and its team has learned not to assume that silence means the mission is over. A weak transmitter can return. A computer can sometimes be restarted. An antenna can drift and later be corrected. The mission has survived by refusing to accept the first explanation. But one day, the explanation will be simple. There will no longer be enough power, control, or functioning hardware to send a useful message home. That moment may come through the transmitter itself. Voyager's electrical supply declines year by year, and every remaining system competes for the same shrinking amount of energy. The radio does not require the largest share of power on board, but communication depends on much more than the transmitter alone. The computer must prepare the data. The antenna must remain pointed toward Earth. The attitude control system must keep the spacecraft stable. Heaters may need to protect fuel lines and other essential components. If any part of that chain fails, the signal can disappear even while other parts of the spacecraft continue working. Communication is not a single device. It is a temporary agreement between aging systems. The antenna is especially important because Voyager is not broadcasting equally in every direction. Its high-gain dish sends a focused beam across billions of kilometers toward the moving region where Earth will be when the signal arrives. The alignment must remain precise despite the distance. A small pointing error near the spacecraft can become an enormous miss by the time the radio beam crosses the solar system. Voyager still carries small thrusters that help maintain this orientation, but they depend on limited fuel and functioning valves. The spacecraft does not need much propellant to continue moving forward. Its momentum will carry it through space for ages. It needs fuel, mainly to control where it faces. This creates one of the strangest possible endings for a mission. Voyager may stop speaking not because it can no longer travel, but because it can no longer turn its attention toward home. The spacecraft could remain electrically active in some limited way. A computer might still cycle. A sensor might still respond. The transmitter might even produce energy. Yet if the antenna no longer points correctly, Earth would hear nothing. The mission would end from our point of view. The machine would continue without us. There is no easy way to know immediately which part failed. Every message received on Earth already describes Voyager as it was many hours earlier. When a reply does not arrive, the team must wait, send another command, and wait again. The distance delays not only communication, but certainty. Silence takes time to confirm. A missing signal could mean the spacecraft has stopped transmitting. It could mean the antenna has moved away from Earth. It could mean the radio frequency has shifted beyond the expected range. It could mean a computer has produced unusable data, while the carrier remains present. Each possibility asks for a different response. The people listening may spend weeks trying them. This is how the final contact could stretch into a long period of uncertainty. The last successful transmission may be recognized only later, after every reasonable attempt to restore the connection has failed. By then, the signal will already belong to the past. The last data packet might contain nothing dramatic: a temperature, a voltage, a magnetic field measurement, a small piece of information about plasma waves in interstellar space. It may not look like a farewell, because Voyager was never designed to say goodbye. The spacecraft does not understand the symbolic weight of its final transmission. It records, stores, and sends according to the commands and systems available. Meaning is added on Earth. To the machine, the last message is simply the last task it was able to complete. To humanity, it would close. one of the longest conversations ever maintained with a distant object. That conversation began when Voyager was still among the planets. Signals carried close views of Jupiter's clouds, volcanic eruptions on Io, the structure of Saturn's rings, and the hazy atmosphere of Titan. Later, the spacecraft turned its cameras back toward the solar system and captured the family portrait that included Earth as a tiny point in sunlight. The images ended long ago. The communication continued. For decades after the cameras were switched off, Voyager remained connected through numbers rather than pictures. It reported the solar wind, particles, magnetic fields, and the slow approach to the heliopause. Then it crossed into interstellar space and continued measuring a region that had never been sampled directly. The final signal would end this direct connection between a working human machine and the space beyond the sun's protective bubble. After that, interstellar space would still surround Voyager. We would simply stop receiving its description. This absence can be difficult to understand because the spacecraft will not vanish. Telescopes will not suddenly see an empty place. Voyager is already far too small and faint to be photographed directly from Earth at its distance. Our knowledge of it depends almost entirely on the radio signal and on calculations of its trajectory. When the signal ends, the spacecraft becomes invisible in a practical sense. Its position can still be predicted. Its condition cannot. We may know where it should be, while knowing nothing about what remains active on board. At first, orbital calculations can follow the path with great confidence. Voyager's velocity is well measured, and deep space contains little that would rapidly alter it. The spacecraft will continue moving in the direction established by its planetary encounters, while the gravity of the galaxy and distant stars slowly shape the larger path. But prediction is not observation. As decades become centuries, small uncertainties grow. The exact pressure of interstellar material, tiny gravitational influences, and unmeasured changes in motion gradually widen the range of possible positions. Voyager will still be somewhere inside that range. No one will hear it confirm where. This is the moment when the spacecraft changes from an active mission into a historical object. While communication exists, Voyager remains part of the present. Engineers can influence it. Scientists can learn from it. Decisions made on Earth can still change which instrument works and how the spacecraft uses its remaining power. When communication ends, all influence ends with it. No future command will alter the machine. No correction will change its orientation. No new software will work around another failure. Voyager will become physically unreachable and technologically closed. The spacecraft will carry every decision made before the silence and none made after it. This gives the final command a strange importance. The last instruction received by Voyager may remain stored or acted upon long after Earth stops hearing the response. Perhaps it will adjust an instrument. Perhaps it will change a heater setting. Perhaps it will ask the spacecraft to begin transmitting once more. The command will cross the darkness and reach a machine at the edge of its life. Whether Voyager obeys may never be known. The people who send it might understand that they are possibly speaking for the last time, yet they would still use the precise language of engineering. A command cannot be sentimental. It must be correct. The spacecraft does not respond to emotion, only to properly formatted instructions. That contrast has followed Voyager from the beginning. Human beings see it as an explorer, a messenger, and a survivor. The machine itself experiences none of these identities. It does not feel distance, age, loneliness, or pride. It processes electrical signals in an environment that would kill any unprotected human instantly. The loneliness belongs to the people imagining it. The silence belongs to both. After the final message, Earth may continue transmitting for a while. Powerful antennas could send commands toward the predicted location, even if no answer returns. The signal would spread outward and eventually pass over Voyager if the alignment remained close enough. Those commands would reach the spacecraft long after they were sent. If the receiver still worked, some might be understood. If not, the radio energy would pass by unnoticed and continue into interstellar space. The conversation could become one-sided before it truly ends. Earth speaks. Voyager gives no sign that it heard. Eventually, the practical effort would stop. Antenna time is valuable, and the Deep Space Network supports many missions across the solar system. At some point, repeated silence would make further contact attempts difficult to justify. The tracking schedules would change. The final team would preserve the records. Voyager would leave daily operations and enter history. The transition might feel too quiet for a mission of such scale. There would be no landing ceremony, no recovered capsule, and no final photograph. The spacecraft would not return to a museum. It would continue moving through a region where no human observer is present. Its ending would happen entirely through absence. The final signal does more than end the science. It removes the last direct proof that Voyager still exists in a recognizable working state. Until then, every transmission says that at least part of the spacecraft survived the journey. Afterward, survival becomes an assumption based on physics. The spacecraft may pass through regions where the density of gas changes. It may move near stars that did not appear significant when the mission began. The galaxy itself will evolve around it. Stars will be born and die. Orbits will shift. The sun will age. Voyager will not measure any of it. Its instruments will be cold structures attached to a silent frame. Yet the motion will continue because no active system is required to preserve it. This is the same physical simplicity that allowed the spacecraft to travel so far during its mission. Once accelerated, it keeps going unless gravity or collision changes the path. The silence removes information. It does not remove velocity. That is why the end of communication is not the final scene. It is the opening of a much longer, darker part of the journey. Voyager has spent decades becoming the most distant active machine linked to Earth. After the final signal, it begins becoming something else. One of the oldest objects humanity has ever sent into nature, and then lost forever. The spacecraft will move beyond the reach of commands, beyond the life of its power source, and eventually beyond the time in which its original mission is easily remembered. But before it can become a relic wandering the galaxy, it still has to cross the vast outer territory of the system that launched it. Its radio will fall silent near the beginning of that passage. The long exit itself will take tens of thousands of years, and while Earth begins living without Voyager's voice, the silent spacecraft will still be moving through the farthest edges of home. Voyager 1 crossed the heliopause in 2012, leaving the vast bubble shaped by the solar wind and entering the space between stars. In one important sense, it had passed beyond the sun's immediate atmosphere. The particles around it changed, the magnetic environment changed, and the spacecraft began measuring material that did not originate in the same way from our star. The heliopause marks the region where the outward flow of charged particles from the sun is finally overcome by the surrounding interstellar environment. It is a real and measurable boundary, yet it is not the limit of the sun's gravity. Far beyond it, objects can still remain loosely bound to the solar system, moving around the sun on paths so large that a single orbit may take millions of years. No spacecraft has seen it directly. Its existence is inferred from the long, narrow paths of comets that sometimes fall toward the inner solar system from enormous distances. These icy bodies appear to come from a vast reservoir surrounding the sun in every direction, not a flat disk like the planets and most asteroids. There would be no crowded field of comets filling the windows, no sudden change in the darkness, and probably no clear moment when the crossing began. Individual objects may be separated by distances so large that Voyager could move through the region for thousands of years without passing close to anything substantial. Its inner edge is thought to begin roughly 1,000 times farther from the Sun than Earth is. Its outer regions may extend tens of thousands of times farther still, perhaps approaching the distance where the gravity of passing stars and the Milky Way begins to compete strongly with the weak pull of the Sun. At its present speed, the spacecraft may need around 3 centuries merely to reach the inner region of the Oort cloud. By that time, every active system on board will have been silent for generations. The final engineers who communicated with it will be part of distant history, and the spacecraft will have traveled for far longer without contact than it ever spent as a functioning mission. The passage through the full width of the Oort cloud may take roughly 30,000 years. That estimate is not a countdown to a sharp outer boundary, but it gives a sense of the distance involved. Voyager crossed the planetary region in decades. Crossing the broader gravitational outskirts of the Sunday may require hundreds of centuries. During that long exit, the Sun will continue shrinking in Voyager's sky. It is already too distant to look like the overwhelming disk seen from Earth. Over the centuries, it will become increasingly similar to the surrounding stars, though its known position will still define the direction from which the spacecraft came. There is no single distance where the Sun stops mattering in every sense. Its light weakens according to distance. Its solar wind ended at the heliopause. Its gravity continues much farther. Human definitions divide these influences into useful boundaries, but Voyager's motion passes through them without ceremony. The first centuries after silence would still place Voyager relatively close to the Sun by galactic standards. Radio waves from Earth could cross the distance, even though there would be no functioning spacecraft able to answer. The solar system would remain recognizable as the origin of its path. Its engines are not driving it toward the cloud. The spacecraft moves because of the velocity acquired long ago, particularly during its encounters with Jupiter and Saturn. Those planets changed the direction and speed of the mission so deeply that their influence will still be visible in Voyager's path tens of thousands of years later. This is one reason the journey feels almost unnatural on a human scale. We are used to machines that operate while they move. A car needs an engine, an aircraft needs fuel, and a ship must continue pushing through water. When the power stops, ordinary vehicles slow and remain where the motion ended. Once the spacecraft is silent, its most important function will require no electricity at all. Momentum will continue carrying the structure outward. The dead computers do not need to calculate the route. The antenna no longer needs to face Earth. The thrusters no longer need to fire. For thousands of years, Voyager will cross a region colder and darker than any place humans have visited. The temperature of empty space is not experienced in the same way as cold air on Earth, because there is almost no surrounding matter to carry heat away through contact. The spacecraft will instead lose energy by radiation, until its surfaces settle into a balance with faint starlight, galactic radiation, and whatever weak warmth remains inside its materials. Radiation will continue striking it. High-energy particles will pass through the hull. Microscopic dust grains may hit at great speed. Most will do little, but time creates opportunities for damage. A tiny impact that would be insignificant during the active mission becomes part of a history lasting thousands of years. The golden record may endure better than the electronics around it, protected by its cover and by the emptiness of space. The surface will still age. Radiation can alter materials, and impacts can scar the spacecraft. But there is no oxygen to rust it in the ordinary way. No rain, no soil, and no weather to pull it apart. The chances are favorable because the Oort cloud is so thinly populated. Even if it contains an enormous number of icy objects, that number is spread through an almost unimaginable volume. Voyager is tiny. The comets are tiny compared with the region they occupy. Their paths are separated by emptiness. This is an important correction to the image of a cloud. The name suggests something continuous, like mist, surrounding the solar system. In reality, Voyager would be moving through darkness where the nearest significant body might remain millions or billions of kilometers away. Its path also carries it away from the broad plane of the planets. After the Saturn encounter, Voyager 1 moved northward relative to the ecliptic, the flat region in which most planets orbit. The Oort cloud, however, is believed to surround the solar system in a much more spherical distribution. The ancient comets can approach from many directions because their distant orbits have been disturbed over time by passing stars, galactic tides, and perhaps events dating back to the Sun's early history. The cloud may preserve material from the formation of the solar system, scattered outward when the giant planets were young. Some objects remained weakly attached to the Sun. Others may have been lost entirely into interstellar space. A comet entering the inner solar system develops a glowing atmosphere and tail as sunlight heats its surface. Voyager will experience no such transformation. It has no ice capable of producing a great cloud, and sunlight will only become weaker. By the time it reaches the inner Oort cloud, Earth itself may be deeply changed. 3 centuries are not enough to transform the Sun, but they are more than enough to transform human civilization. Languages, technologies, nations, and institutions can change beyond recognition in that span. Even an advanced spacecraft, sent later, would face an enormous chase. Voyager already has a long head start and continues moving away. A future mission would need to travel significantly faster, survive the distance, and intercept an object that provides no active signal. A few meters of metal in a volume, measured across billions of kilometers, is not a target that can be approached casually. Without the radio beacon, Voyager becomes almost indistinguishable from the darkness surrounding it. Small forces that barely matter across decades may slowly alter the exact route. The gravity of distant stars, the uneven distribution of matter in the galaxy, pressure from radiation, and impacts with dust can all contribute tiny changes. None is expected to turn Voyager sharply. Yet, after thousands of years, the predicted path becomes a corridor rather than a perfect line. This means Voyager may become lost without ever changing direction in a dramatic way. It is not lost because it does not know where it is. The dead spacecraft knows nothing. It becomes lost because no observer can identify its exact location well enough to recover it. Across 30,000 years, even the shape of the nearby stellar neighborhood will change. Stars move relative to one another. The constellations seen from Earth today will stretch and dissolve. The patterns engraved into human culture will no longer match the sky. Voyager's route is often described using a modern constellation, but constellations are only apparent patterns viewed from one moving planet at one moment in galactic history. This becomes important near the outer regions of the Oort cloud. The Sun itself is not stationary, while Voyager escapes. Both travel around the center of the Milky Way. The solar system carries its planets and distant comets along that galactic orbit, while Voyager follows a slightly different motion shaped by its escape from the Sun. The Sun's gravitational hold becomes weaker with distance. Passing stars can matter more. The gentle tidal influence of the galaxy becomes more important. An icy object near the outer Oort cloud can be disturbed and sent inward or stripped away entirely. The meaning of permanently is difficult to hold. Voyager's active mission can be described in years. Its passage through the Oort cloud requires millennia. Its motion through the galaxy extends far beyond the age of recorded history, beyond the survival of most structures ever built, and perhaps beyond the survival of our species in its present form. This contrast makes the Oort cloud more than a distant region. It is the place where Voyager's story stops fitting easily inside human history. The first few centuries may still be imagined as a future connected to ours, 30,000 years, is different. 30,000 years ago, much of the human world was shaped by the last ice age. Agriculture had not yet transformed civilization. No city, spacecraft, written scientific record, or radio antenna existed. If human beings still exist, Voyager may be remembered as an artifact from an ancient technological beginning. The spacecraft may seem impossibly simple, built by a civilization that had barely begun exploring its own planetary system. This indifference is central to the journey. Voyager was given meaning by the people who launched it, operated it, and listened to it. The path itself needs no meaning. Gravity and momentum do not preserve stories. It will pass beyond the densest region of distant comets, if the cloud has the shape our models suggest. The sun's light will become one weak contribution among many stars. Its gravity will still exist, but Voyager will no longer be bound strongly enough to return. At some uncertain point, saying that the spacecraft remains inside the solar system will no longer be useful. Then Voyager will belong more clearly to the galaxy than to the system that produced it. Even this does not mean it will be approaching a new home. Interstellar travel is not a sequence of nearby destinations. Stars are separated by distances so large that an escaping object can wander for ages without entering any planetary system. There will be no braking burn, no orbit, and no active instrument watching the star grow brighter. The spacecraft will pass through another part of the galactic neighborhood exactly as it passed through the Oort cloud. Cold, silent, and unaware. Voyager is not simply chasing it across a fixed sky. Their paths slowly bring them nearer to each other, creating an encounter that exists because both objects travel through the galaxy. By the time this happens, the Oort cloud passage will be nearly complete, the sun will be far behind, and every human voice once carried by the spacecraft will be unimaginably old. Voyager will have spent tens of thousands of years leaving home. Then, it will approach a star it was never truly trying to reach. The star is known as AC plus 79 3888, or Gliese 445, a small red dwarf that is currently more than 17 light-years from Earth. Voyager 1 is not aimed at it in the way a spacecraft is aimed at a planet. There will be no arrival sequence, no braking maneuver, and no moment when the probe enters orbit. The encounter will happen only because both the star and the spacecraft are moving through the galaxy, and their paths will briefly bring them closer together. In about 40,000 years, Voyager is expected to pass within roughly 1.7 light-years of Gliese 445. That distance is close only by the standards of interstellar space. It is more than 100,000 times the distance between Earth and the Sun, far beyond any region where the star would fill the sky or become a destination. Even the phrase, Voyager is heading toward Gliese 445, can create the wrong picture. It suggests that the spacecraft selected the star long ago and has spent thousands of years crossing space toward it. In reality, the star itself is moving rapidly in Voyager's general direction. Much of the future closeness comes from Gliese 445 approaching the path of the spacecraft, not from Voyager chasing the star across a fixed sky. By then, Voyager will have traveled beyond the broad outer region associated with the Oort cloud. The Sun will be far behind it, and the probe will have spent almost all of its existence without power, guidance, or communication. Nothing on board will recognize that another star has become nearer than the Sun. If Voyager still retained its original shape, Gliese 445 might appear brighter than it does from Earth today, but it would not resemble the Sun in the sky. The star is much smaller and dimmer than the Sun, and the spacecraft will remain far outside any planetary system close enough to explore. Modern observations have not revealed a world waiting directly in the spacecraft's path, and even if such planets exist, a passage at more than a light-year would leave them hopelessly distant. The probe would move past the system without touching the space where planets are likely to orbit. A spacecraft visiting another star would need to enter the inner system, where the star's light becomes strong, planets become detectable at close range, and gravity begins to shape the trajectory clearly. Voyager's predicted passage remains in the enormous gap surrounding the star. The spacecraft has no engine capable of changing this. Its small thrusters were designed to control orientation, not to redirect an interstellar trajectory after tens of thousands of years. By the time of the encounter, their fuel will be frozen, leaked away, or trapped inside systems that have been inactive for ages. The star's gravity will pull on the spacecraft, but from 1.7 light-years away, that pull will be extremely weak. It may bend the path by a small amount, adding one more change to a route shaped by distant forces. It will not capture Voyager, bring it into orbit, or turn the spacecraft into a permanent companion of the star. There is something quietly strange about spending 40,000 years approaching an object and never truly arriving. Human journeys are usually defined by destinations. The traveler crosses distance because somewhere ahead there is a point where the movement can stop. This is how motion works on the scale of the galaxy. Stars do not remain arranged in the patterns we see tonight. They travel through space with different speeds and directions, carrying any planets with them. A star that appears far away now may cross closer to the Sun in the distant future. Another that seems nearby may gradually recede. The path cannot be understood by drawing one straight line through a permanent map of the stars. The map itself changes while the spacecraft travels. Gliese 445 is a clear example. From Earth today, it is a faint red dwarf, invisible to the naked eye. Its motion is bringing it closer to our region of the galaxy, and tens of thousands of years from now, it may be much closer to the Sun than it is today. If an observer could watch from somewhere near Voyager, the approach would unfold too slowly to notice during a human lifetime. Gliese 445 would brighten gradually over many centuries, reach a maximum apparent brightness, and then begin fading as the distance increased again. Voyager's own speed is enormous by human standards, around 17 kilometers every second relative to the Sun. It could cross an ocean in minutes and travel around Earth in less than an hour. Yet interstellar distances make that velocity appear almost motionless. This helps explain why the probe is unlikely to collide with a star or planet. The Milky Way contains hundreds of billions of stars, but they are spread across a volume so great that direct encounters are extraordinarily rare. Most objects moving through interstellar space pass through vast emptiness. The image of interstellar travel often focuses on destinations. A ship leaves one system and arrives at another. Voyager shows what happens when no destination is chosen. The spacecraft can travel between stars and still spend almost all of its future closer to none of them in any useful sense. For a short period around the encounter, Voyager may be closer to Gliese 445 than to the Sun. That sounds like a transfer of identity, as though the spacecraft has finally left one star and joined another. Gliese 445 will not hold Voyager in a stable orbit. The probe will not become part of a planetary system. It will simply pass the point where one star is less distant than the other, then continue into another region of the galaxy. The materials in Voyager were formed within the solar system. The machine was assembled on Earth. Its route was shaped by Jupiter and Saturn. The golden record carries the sounds of a world orbiting the Sun. Gliese 445 itself will not remain unchanged forever. Red dwarfs are small, efficient stars that can burn for extremely long periods, far longer than stars like the Sun. When Voyager passes nearby, the star should still be active, continuing a lifetime that may extend for trillions of years. The encounter therefore takes place early in the larger story of the video. 40,000 years is immense compared with human civilization, but it is almost nothing compared with the time left before the Sun dies. This creates a powerful contrast in scale. To reach Gliese 445's neighborhood, Voyager needs tens of thousands of years. To reach the time when the Sun becomes a red giant, it must continue through more than 100,000 times that span. After Gliese 445, the spacecraft will continue along a path influenced by the galaxy. Other stars may pass closer in the centuries and millennia that follow. Some future encounters can be estimated from modern stellar measurements, but those predictions become less certain as time grows. The positions and velocities of nearby stars are measured with remarkable precision, yet tiny uncertainties expand across hundreds of thousands of years. The gravity of stars, clouds, and the Milky Way adds further changes. A future close passage can be predicted as a range rather than a perfectly known event. This uncertainty is not a failure of physics. The laws remain consistent. The problem is that a tiny uncertainty in the present becomes a large difference after enough time. If a star's measured velocity is slightly wrong, its predicted position hundreds of thousands of years later can shift by an enormous distance. Gliese 445 remains one of the most familiar names in descriptions of Voyager's journey because the encounter is close enough in time to estimate and simple enough to imagine. But it should not be mistaken for the spacecraft's final destination or most important future event. The golden record will still face no particular direction. The antenna may no longer point toward Earth or anywhere meaningful. Voyager could tumble slowly if its orientation control systems fail and external forces disturb its attitude. The Sun would be one star among many. Gliese 445 would brighten and fade. Other stars would shift over time. The background of the Milky Way would surround the spacecraft, but even that background would not remain fixed. Voyager's engraved maps and astronomical references were designed around physical constants and the positions of pulsars, not around the temporary shapes of constellations. The people who made the golden record understood that familiar star patterns would not survive forever. This becomes important because Gliese 445 is often described as being in Ursa Minor, or sometimes by a position associated with another modern constellation. Those names describe how the star appears from Earth during our era. They are labels placed on a changing sky. 40,000 years from now, the pattern called Ursa Minor will be distorted. The stars that form it will have shifted relative to one another. Gliese 445's own position will be different. The old constellation will no longer guide an observer in the same way. The same will happen to every constellation known from Earth. Orion will stretch. The Big Dipper will lose its familiar form. Nearby stars will move noticeably over tens of thousands of years, while more distant stars shift more slowly. The spacecraft begins beneath one sky, passes Gliese 445 beneath another, and will still be traveling when both arrangements have disappeared. This makes the encounter less like reaching a landmark and more like crossing a changing current. Nothing waits in the exact place where we first observed it. The star comes toward the spacecraft moves outward, and the Sun carries Earth through the galaxy at the same time. Had Voyager traveled at a different speed, the encounter might not happen. Had Gliese 445 moved along a slightly different path, the closest approach would be farther away. The future passage exists because two histories happen to cross within the same broad period. For the spacecraft, there will be no story at all. Voyager will not distinguish approach from departure. It will not know when Gliese 445 becomes the nearest star, or when the Sun takes that place again. Its code structure will continue along the path with no awareness of distance. No likely planet will rise ahead. No star will surround it with warmth. No civilization, if one exists there, is expected to notice a small dark object crossing the outer emptiness. The encounter is close enough to name and far enough to remain almost complete isolation. By then, the sky around the spacecraft will already be different from the one seen at launch. The sun will have changed position among the stars. Familiar constellations will have bent into new shapes, and the direction marked as home will no longer sit inside the same pattern. The passage near Gliese 445 therefore does more than place Voyager beside another star. It marks the beginning of a deeper change in the journey, the slow disappearance of the sky that once connected the spacecraft to Earth. And after that distant near miss, even the sky around Voyager will no longer resemble the one it carried away from Earth. The stars do not remain where we see them. From Earth, the constellations appear almost permanent, because a human lifetime is too short to reveal most of their motion. Orion rises in winter. The Big Dipper turns around the northern sky. Familiar patterns return year after year, and the small changes are hidden by the scale of the distance. Voyager will travel long enough for that appearance of permanence to fail. The stars that form a constellation are not usually close to one another in space. They only seem connected because we view them from one particular place. One star may be tens of light years away, while another lies hundreds of light years behind it. Yet their light reaches Earth along directions that place them beside each other in the sky. The pattern exists in perspective. Change the viewpoint, and the shape begins to break. Voyager has already moved far enough that the nearest stars would appear slightly shifted compared with the sky seen from Earth. The difference is still small, but it grows as the spacecraft continues outward. Over tens of thousands of years, the change in viewpoint combines with the motion of the stars themselves. The sky is altered from both sides. Voyager moves through the galaxy. The stars move around it. A constellation that once looked stable begins to stretch, bend, and lose its familiar proportions. The stars do not disappear at the same time, but the lines humans imagined between them stop making sense. This would not happen in one dramatic moment. No constellation would suddenly collapse. The changes would be slow enough that an observer living beside the spacecraft could spend an entire lifetime without seeing the pattern noticeably shift. Some of the brightest stars in the current sky will no longer exist by the time the sun approaches the end of its life. Massive stars burn their fuel quickly. A star that appears stable tonight may explode or collapse long before Voyager reaches the distant future, described by the title. Others will remain, but drift elsewhere. Red dwarfs may continue shining for trillions of years, while large blue or white stars disappear after much shorter lives. The future sky is shaped not only by movement, but by stellar aging. Voyager will pass through a gallery that is always replacing itself. The spacecraft cannot watch this transformation. Its cameras were shut down decades before it left the planetary region, and no active system will remain through these enormous spans of time. Yet the change still matters, because it removes every familiar visual connection to the world that launched it. The sky around Voyager will stop resembling Earth's sky. The sun will remain somewhere behind, but even identifying it would become difficult without precise knowledge. It will look like one star among many, slowly changing position as Voyager and the solar system follow different paths through the Milky Way. From the spacecraft's future location, the Sunday may no longer sit near the same neighboring stars seen around it today. The background will have rearranged. The idea of turning around and looking homeward becomes less simple when the sky itself no longer provides familiar landmarks. On Earth, sailors once used the stars because their patterns changed very little within a human journey. A fixed sky could reveal direction. Voyager enters a future where no human pattern remains fixed long enough to serve that purpose. A map based only on constellations would slowly become useless. This is why the Golden Record does not depend on familiar star shapes to reveal where Voyager came from. The cover includes a diagram based on pulsars, rapidly rotating remnants of dead stars that send regular signals into space. Their characteristic timing was intended to provide a more durable cosmic reference than a drawing of the night sky. The same is true for Earth's position. Our planet does not leave a stationary mark in space. The solar system travels around the center of the Milky Way at hundreds of thousands of kilometers per hour, completing one galactic orbit over hundreds of millions of years. Since Voyager's launch, the Sun has already moved an enormous distance through the galaxy. Earth has traveled with it. Voyager also moves around the galaxy, but not in exactly the same way. It escaped the Sun with additional speed and a different direction. At first, this difference is small compared with the shared motion inherited from the solar system. Over time, the separation grows. The spacecraft does not leave the galaxy by escaping the Sun. It remains gravitationally bound to the Milky Way, carrying almost all of the galactic motion it had when it launched. This means Voyager's future is not a straight line extending forever from the present location of the Sun. The Sun will not remain behind at one fixed point. Both objects continue moving around the galactic center. The line between them changes. An illustration showing Voyager traveling away from a stationary solar system can be useful over short times, but across millions or billions of years, it becomes misleading. The entire scene is in motion. The Sun curves along its galactic orbit. Voyager follows another curved path shaped by the same galaxy. The spacecraft may move farther from the Sun while still traveling through the same broad region of the Milky Way. The distance grows inside a larger shared journey. This is where the disappearance of the familiar sky becomes more than a visual change. It reveals that Voyager is no longer moving through a map centered on Earth. The spacecraft belongs to the galaxy's motion now. The stars are not a background behind the journey. They are part of the journey. Every nearby star has its own path. Some will pass closer to Voyager, others will recede. A dense molecular cloud may alter the environment. The gravitational pull of the galactic disk and central regions slowly shapes the spacecraft's orbit. No single encounter has to be dramatic. The combined effect lasts for billions of years. The Milky Way is not empty space with stars placed inside it. It is a gravitational system made of stars, gas, dust, dark matter, and a central mass distribution that guides the motion of everything within it. Voyager becomes one extremely small object following that system. The spacecraft was launched from Earth, but the speed of the rocket is only a small addition to the motion it already possessed. Before launch, Voyager was moving with Earth around the Sun, and with the Sun around the galaxy. The rocket did not create all of its velocity, it changed part of it. Jupiter and Saturn changed it again. The resulting path allowed the spacecraft to escape the Sun, but not the Milky Way. The energy required to leave the galaxy is far greater than the energy Voyager carries. So the probe does not travel forever into an absolute outward direction. It begins a new orbit around the Milky Way. That orbit is not expected to be neat or easily described. Voyager is not a star with a massive planetary system. It is a small, cold body, influenced by the galaxy and by any close stellar passages that occur over time. Most of those influences are weak. Given enough time, weak influences matter. A passing star could alter Voyager's direction slightly. The gravity of a molecular cloud could add another small change. The uneven mass of the galactic disk could bend the path over immense distances. The spacecraft's future route becomes a product of encounters that cannot all be predicted today. For the first million years or so, modern measurements allow scientists to estimate several possible stellar approaches. Beyond that, uncertainty grows. Not because the physics changes, but because no measurement is perfectly exact. A tiny uncertainty in a star's present speed becomes a large uncertainty in its position after millions of years. The same is true for Voyager. A difference too small to matter today can shift the spacecraft's future path by light years across deep time. This does not mean Voyager's motion becomes random. It means the exact path becomes unknowable from our present information. The spacecraft will be somewhere specific. Our prediction spreads across possibilities. This is a quiet limit on the question asked by the video. We can describe where Voyager may pass in the next tens of thousands of years. We can explain how the Sun will change billions of years from now. But placing the spacecraft at one exact coordinate when the Sun dies is beyond any honest calculation. The familiar constellations will disappear because they were never fixed to begin with. New apparent patterns will form for any observer located near Voyager, though no human names will be attached to them. Some stars will look brighter because the spacecraft has moved closer. Others will fade into the background. The Sunday may become too faint to distinguish without instruments. There will be no visual sign that one small star once supported the world, represented on the golden record. This is what makes the future around Voyager feel empty, even while surrounded by stars. The Milky Way contains hundreds of billions of them, but abundance across an enormous volume still produces isolation. The probe may travel through multiple galactic orbits without entering another planetary system. It can be among stars and remain far from all of them. The constellations seen from Earth create the impression that stars are grouped closely together. Once those patterns dissolve, the true scale becomes clearer. The stars are separated by light years, and Voyager crosses those distances at a speed that is fast for a machine, but slow compared with light. By the time the Sun begins to leave its stable life, Voyager may have completed only a small number of journeys around the Milky Way. One galactic orbit takes hundreds of millions of years, so the remaining lifetime of the Sun allows enough time for the spacecraft and solar system to circle the galaxy many times. They will not follow the same orbit. Each passage reshapes their relative positions. The Sunday may cross regions of the galaxy different from those it occupies today. Voyager may travel above or below the main disk before being drawn back. Nearby stellar neighborhoods will form and disperse. The phrase, "far from home," becomes difficult to define after so many galactic revolutions. Home itself has moved. The Sun is no longer near the stars that surrounded it when Voyager launched. Voyager is no longer moving through the sky shown on the golden record. The separation is not just a distance between 2 points. It is a separation between 2 evolving paths. This is why the disappearance of the familiar sky matters to the larger story. The spacecraft does not merely travel farther from Earth. It enters a future in which the reference points of departure have been rearranged. The old constellations cannot guide it. The Sun cannot remain a fixed beacon. Even the predicted stellar encounters eventually become uncertain. What remains is motion inside the Milky Way. Voyager will continue because the galaxy carries it, just as the galaxy carries the Sun, the planets, and every star that once formed the night sky above Earth. The spacecraft will no longer be crossing a map we recognize. It will be following its own long curve through the galactic dark. And once the familiar sky has completely dissolved, Voyager's future can only be understood as a new journey around the Milky Way itself. The spacecraft is no longer simply moving away from the Sun. It is joining the motion of the galaxy. That distinction changes the entire picture. A drawing often shows Voyager traveling outward along a straight line, while the solar system remains behind at the center. Over a few decades, that image is useful. Over millions of years, it becomes wrong. The Sun does not stay in one place. It travels around the center of the Milky Way at hundreds of thousands of kilometers per hour, carrying Earth, the planets, and the distant remains of the solar system with it. Voyager inherited most of that motion before it ever launched. The rocket did not begin from stillness. It began from a moving planet orbiting a moving star inside a moving galaxy. The gravity assists at Jupiter and Saturn added speed and redirected the spacecraft enough to escape the Sun. But they did not free it from the Milky Way. Voyager does not carry nearly enough energy to leave the galaxy. It remains part of the same vast gravitational system as the Sun. From this point forward, The spacecraft and the solar system follow separate paths around the galactic center. Their motions are similar because they began together, but they are not identical. Voyager carries additional speed and a direction tilted away from the broad plane of the planets. Over time, that difference becomes distance. The two paths slowly separate. This is not like one object moving away from another across an empty floor. Both are curving through a complex gravitational field. The Sun follows an orbit through the galactic disk, rising slightly above and below it over immense periods. Voyager may follow a somewhat different curve, shaped by its velocity, the pull of the Milky Way, and the influence of objects it passes. Nothing about that path is perfectly simple. The Milky Way is not a smooth, uniform circle of stars. Its mass is distributed through the disk, spiral arms, central bulge, gas clouds, star clusters, and a much larger halo of dark matter. All of this contributes to the gravity that guides motion. Voyager responds to that combined field. The spacecraft is almost weightless in comparison with stars and planets. But gravity does not ignore small objects. It bends Voyager's route in the same way it shapes the orbits of comets, stars, and clouds. The path is real even when no one can observe it directly. For a time, the route remains predictable. Scientists know Voyager's present velocity and direction with great precision. They can model the gravitational influence of the Sun and nearby stars and project the spacecraft's movement into the future. But every prediction has limits. The farther the calculation extends, the more small uncertainties matter. A tiny error in the measured speed of a nearby star may shift its predicted future position by a vast distance. A close pass that is expected to miss Voyager by several light-years could occur slightly nearer or farther. The difference may alter the spacecraft's trajectory by a small amount. One small change becomes the starting point for the next calculation. Then, another star passes. Another gravitational influence is added. Across millions of years, the route branches into a growing range of possibilities. Voyager will still occupy one exact position at every moment. It is our knowledge that spreads. This is why the question of where Voyager will be when the Sun dies cannot be answered with a single reliable coordinate. The laws of motion remain understandable, but the measurements available today cannot preserve exact certainty across billions of years. Too many small effects have time to grow. The spacecraft may pass through regions of the galaxy that are denser than the local neighborhood around the Sun. It may move closer to stars that are still too distant to be called destinations. It may cross through thin clouds of gas and dust that barely affect its structure but add tiny changes to its motion. None of these events has to be dramatic. Together, they write the future path. A molecular cloud could alter the gravitational environment over a long period. A star passing within a fraction of a light-year could bend the route more noticeably. Even a distant encounter can matter when the spacecraft has billions of years ahead. Voyager's speed makes it resistant to weak capture. A passing star is unlikely to pull the probe into orbit unless the geometry is unusually close and slow. More often, gravity would change the direction slightly, leaving Voyager on another galactic path. The spacecraft would continue, only the curve would be different. This process has no final destination. Voyager may pass through one region of the Milky Way, move into another, and later return to a similar part of the disk after completing a galactic orbit. One orbit around the Milky Way takes the Sun roughly a few 100 million years. Voyager's period would not be exactly the same, but the timescale is similar enough to reveal the scale of what lies ahead. Before the Sun reaches the end of its life, Voyager may circle the galaxy many times. Each orbit carries it through a changing Milky Way. Stars are born in dense clouds. Others expand, explode, or collapse. Clusters spread apart. Spiral structures shift. The galactic environment, seen during one orbit, will not be identical during the next. Voyager's path continues through a system that is evolving around it. The spacecraft will not notice any of this. Its instruments will be inactive, its power gone, and its orientation no longer controlled. The antenna may point toward no meaningful location. The body may rotate slowly, influenced by tiny torques from radiation or past mechanical imbalance. From one side, the spacecraft faces the galactic center. Much later, another side does. The golden record turns with it. There is no stable forward direction in the human sense. Voyager is not a ship with a window looking toward a destination. It is an object moving through a gravitational orbit, while its structure may slowly tumble. The idea of a head exists only along the path. The galaxy itself fills every direction. The title asks about the moment the sun dies, but even that moment is not perfectly sharp. The sun's final transformation unfolds over a long sequence. It leaves its stable phase, expands into a red giant, sheds outer layers, and becomes a white dwarf. Voyager's location changes throughout that process. There is no single frozen scene. The spacecraft may complete part of another galactic orbit, while the sun moves through its final stages. The dying of a star takes much longer than a human life, and much longer than any spacecraft mission. The event is an era. Voyager crosses distance through all of it. To understand where the probe might be, the question must therefore be widened. The important fact is not a coordinate, but a condition. Voyager will almost certainly be somewhere else in the Milky Way, following a path that has been shaped by billions of years of galactic motion. It will no longer be close to the sun in any meaningful sense. It may not be near the same stars. It may not occupy the same region of the galactic disk. The spacecraft's path could have been changed by encounters we cannot yet predict. The exact answer is hidden inside events that have not happened. Yet the broad answer remains clear. Voyager will still be moving around the Milky Way unless something destroys it, captures it, or throws it onto a very different path. The galaxy becomes its long-term home. Not a home in the human sense, but the gravitational system that contains its journey. Voyager left Earth. It escaped the sun. It did not escape the Milky Way. This progression matters because every stage removes one layer of the familiar. Earth was the world that built it. The solar system was the structure that accelerated it. The galaxy is the final environment that continues to shape it. After all, active purpose is gone. The spacecraft becomes a natural orbiting object in everything except origin. It moves like debris. It responds to gravity like a small asteroid. It carries no visible sign of intention unless someone finds it closely enough to recognize the engineering. From a distance, Voyager is just another cold object traveling through the disk. Its human meaning is hidden in its construction. The golden record is hidden beneath its cover. The history of Jupiter, Saturn, and Earth is not written into its motion in a way the galaxy can read. Meaning survives only if there is an observer capable of understanding the object. Without one, the spacecraft follows the same rules as dust, rock, and ice. This does not make the journey less remarkable. It makes it stranger. A machine created for a brief planetary mission becomes part of a galactic orbit that may continue longer than the planet that made it remains habitable. The transformation happens gradually. During the active mission, Voyager is a scientific instrument. After silence, it is a relic. After enough time, it becomes part of the moving population of the Milky Way. The name remains on Earth. If Earth still remembers it, the object continues without needing the name. Across each galactic orbit, the direction toward the sun changes. The solar system may appear in another part of Voyager's sky, then fade among different background stars. Any simple idea of behind or ahead loses meaning. The original departure direction belonged to one moment. The galactic path carries the spacecraft through many new orientations. Voyager's journey is not an arrow extending forever away from home. It is a curve within a much larger curve. This is why the future cannot be shown accurately by holding the Milky Way still. The Sun is moving around the center. Voyager is moving too. The stars between them follow their own paths. The entire map is alive with motion. This is why exact coordinates fail so completely on the timescale of stellar death. The question seems to ask for a place, but the place itself evolves. The stars move, the galaxy changes, Voyager's orbit changes with it. The Sun's path changes too. The only stable part of the picture is that both continue obeying gravity. The spacecraft may be billions of kilometers from the nearest star or a few light years from one when the Sun enters its red giant phase. It may be crossing a quiet region of the galactic halo or moving through a richer part of the disk. No present calculation can select one scene honestly. What can be understood is the separation of histories. Voyager follows one galactic future. The solar system follows another. For thousands of years, the difference is mostly distance. For millions, it becomes a different stellar neighborhood. For billions, it becomes a different place in a changing galaxy. The story of Voyager is therefore not only about a probe traveling outward, it is about two paths that began together and then slowly lost their connection. One path belongs to a silent machine. The other belongs to a star carrying the world that created it. While Voyager circles the galaxy, the Sun continues aging. Its light slowly changes. Its planets continue orbiting. Earth remains behind, inside a system that will not stay as Voyager remembers it. The spacecraft's galactic journey can continue almost indefinitely, but the solar system has its own clock. Long before the Sun dies, its gradual evolution begins altering the worlds around it. Voyager may survive as an object because it needs almost nothing. Earth survives only while many conditions remain balanced. Those conditions will not last forever. And as Voyager begins its silent orbits around the galaxy, the solar system it left behind will begin its own much slower transformation. At first, almost nothing will appear to change. The planets will continue moving through the same broad paths. Jupiter will turn beneath its storms. Saturn's rings will spread around the planet in sunlight. Earth will complete another year, then another, while the Sun rises and sets with the same familiar brightness. But the solar system is not permanent. It only changes too slowly for a human life to notice. The Sun has been shining for billions of years, and it still appears stable because the processes inside it unfold on timescales far longer than history. Yet every second, hydrogen in the core is being converted into helium. The fuel is not disappearing suddenly, but the balance at the center of the star is gradually changing. As helium builds up, the core becomes denser and hotter. That heat causes the Sun to produce slightly more energy. The increase is slow enough to seem harmless. Over hundreds of millions of years, however, a small rise in solar brightness becomes a major change for the planets nearby. Voyager will not see the difference. Its dead instruments will be traveling through another part of the galaxy, while the sunlight reaching Earth grows stronger by degrees. The Sun of the distant future will still look like the Sun. It will simply be brighter. This is one of the most unsettling parts of the solar system's future, because the transformation begins long before the dramatic red giant phase. Earth does not need to wait for the Sun to expand across the sky before becoming hostile to life. A modest increase in energy can change the climate of an entire planet. More sunlight warms the surface. Warmer air holds more water vapor. Water vapor itself traps heat, strengthening the warming further. The oceans respond slowly, but they contain most of the water that makes Earth habitable. Across immense time, the planet's stability begins to weaken. The exact sequence depends on complex climate feedbacks, and no single date can describe the end. Yet many models suggest that long before the Sun becomes a red giant, Earth may lose the conditions that allow large, complex life to survive. The atmosphere will change. The oceans will begin retreating. The familiar blue world carried on Voyager's golden record will become something else. This change may begin around 1 billion years from now, though the details remain uncertain. That is a vast span compared with human civilization, but it is still early compared with the Sun's remaining lifetime. Voyager could complete several galactic journeys while Earth is slowly transformed. The spacecraft may still exist as a dark object when the planet that built it no longer has forests, oceans, or breathable air. Earth's first great loss may not be destruction. It may be habitability. As the Sun brightens, weathering processes can remove more carbon dioxide from the atmosphere. Plants depend on carbon dioxide, and different forms of life tolerate different amounts. But eventually the concentration may fall too low for many plants to survive. The loss would move through the biosphere. Plants support food webs. They also help shape the atmosphere. As they disappear, complex ecosystems may follow. Microbial life could remain much longer in protected environments, perhaps underground or near the last stable sources of water. Life on Earth has survived extraordinary changes before, and simple organisms can endure conditions that would be impossible for humans. But even the strongest survivors depend on limits. The sun continues brightening. The oceans continue losing water. Ultraviolet light breaks water vapor high in the atmosphere into hydrogen and oxygen. The light hydrogen can escape into space, removing part of the planet's water permanently. A world can lose an ocean slowly enough that no single generation sees it happen. Over geological time, the loss becomes complete. Earth may come to resemble a dry, heated planet beneath a brighter star. The continents remain for a while. Mountains erode. Empty ocean basins stretch across the surface. The atmosphere becomes hotter and more difficult to retain in its familiar form. There may be no single final day for life. Habitats simply become fewer. The last organisms retreat into smaller regions. Eventually, even those regions fail. Voyager will not know that the planet shown on its record has changed. The disk may still carry the sound of waves. The actual oceans may be gone. The record may still preserve rain, birds, and human voices, while the Earth itself becomes silent. This contrast grows stronger because Voyager's physical environment may change very little during the same period. The probe needs no liquid water, atmosphere, or stable climate. It can remain a damaged object in interstellar space, while a living planet becomes unable to support life. The machine survives because it is already dead. Earth is vulnerable because it is alive. A biosphere requires balance. Temperature, water, chemistry, and energy must remain within ranges that allow complex processes to continue. Voyager requires only that nothing large enough strikes and destroys it. The spacecraft's needs are almost zero. Earth's are enormous. This does not mean Voyager is stronger than the planet. Earth can absorb impacts and repair damage through geology, chemistry, and life. It has already survived events that would have shattered a spacecraft. But Earth's ability to support living systems depends on the sun remaining within a narrow range. That range does not last forever. Farther out, the giant planets remain colder and less affected at first, but they are not frozen in time. Saturn's rings may not survive for billions of years in their current form. Ice and rock slowly fall into the planet or spread outward. Small moons disturb the ring system. Impacts and radiation darken material. The rings visible in Voyager's images may disappear long before the sun dies. Future Saturn could still be a giant world with many moons, but without the structure that made it instantly recognizable. Voyager's photographs would then preserve a planetary system that no longer exists. The same is true of storms, atmospheres, and small moons. Jupiter's great red spot may change or vanish. Volcanic worlds continue resurfacing. Icy moons may lose internal heat. Orbits can shift through long gravitational interactions. The outer planets appear stable because their changes are slower than observation. Deep time reveals that stability is only a phase. The small bodies of the solar system also continue moving. Comets are disturbed by planets, passing stars, and the gravity of the galaxy. Some fall inward, others are thrown away. Asteroids collide and break into new families of fragments. The distant Oort cloud is slowly reshaped by the environment around the Sun. Voyager once crossed through the outer region of that system. After millions and billions of years, the cloud itself may have a different form. Passing stars can strip away distant comets or send them toward the inner planets. The Sun does not travel through the galaxy alone in a perfectly empty corridor. Its neighborhood changes as stars approach and recede. Most encounters are distant. Occasionally, one may come close enough to disturb the solar system significantly. A nearby stellar passage could alter the orbits of outer comets. It might create a long period of increased comet activity in the inner system. A closer event, though far less likely, could disturb planetary orbits. No exact future encounter can be predicted across billions of years. The uncertainty becomes part of the story. The solar system may remain broadly stable until the Sun's final stages, or it may experience changes we cannot calculate from the present. The planets move through a gravitational arrangement that is stable for long periods but not mathematically guaranteed forever. Voyager escapes many of these changes because it is no longer bound to the Sun. The same freedom that carries it into isolation also removes it from the final instability of its birthplace. It will not be warmed by the brighter sun. It will not see the oceans disappear. It will not be affected by the moon's retreat or Saturn's fading rings. The spacecraft has left the system that gave its images meaning. Every scene recorded during the planetary mission becomes older than the worlds it shows. Jupiter may still exist, but its atmosphere will not hold the same storms. Saturn may remain, but its rings may be gone. Earth may orbit the Sun, but no longer appear blue. The Voyager archive becomes a record not only of distance, but of a vanished era. This is what an ancient spacecraft would carry through the galaxy. Not a permanent description of the solar system, but a snapshot of one brief arrangement. The planets were photographed at particular moments. The Earth was heard during one living age. The golden record did not capture what the solar system is. It captured what it was then. Across the next billion years, the Sun will be roughly 10% brighter than it is today. That increase sounds small, but Earth's climate is sensitive to the energy it receives. A planet, balanced between frozen water and boiling oceans, does not need the star to double in brightness before becoming unrecognizable. Small changes sustained for long enough can cross irreversible thresholds. Once the upper atmosphere becomes rich in water vapor, the loss of hydrogen can continue. Once oceans shrink, their ability to regulate climate weakens. Once ecosystems collapse, they may not return even if some later condition temporarily improves. The future does not need a sudden catastrophe. It can be built from one slow change that never reverses. This is how the solar system moves toward the death of the Sun. Not through a quiet age followed by one final explosion, but through stages. The Sun brightens, Earth dries, the Moon recedes. Planetary surfaces and atmospheres change. The outer system evolves. Only much later does the star begin the transformation that can be seen across interstellar distances. Voyager's journey and the solar system's aging happen on different clocks, yet both are moving toward that later era. The spacecraft circles the galaxy, perhaps passing near stars and drifting through regions that cannot be predicted. The Sun remains on its own galactic path, carrying a planetary system that slowly loses the form Voyager knew. The Sun itself remains recognizable through much of this transformation. Even as it brightens, it continues fusing hydrogen in its core. It does not yet swell into a giant or lose its outer layers. The change is internal and gradual. Helium accumulates, the core contracts, the surrounding layers heat. The star adjusts its balance by shining more strongly. This stable-looking phase has a limit. Eventually, the central hydrogen becomes too depleted for the sun to continue as it has for most of its life. The core changes more rapidly. The outer layers begin responding. What had been a slow increase in brightness becomes the beginning of a far larger transformation. By then, Earth's habitability is likely to have ended long ago. The red giant phase is not what removes the world we know. It arrives after that world is already gone. This distinction makes the future more unsettling. The sun does not need to touch Earth to end its living era. It only needs to change gradually, as every normal star eventually does. Voyager leaves behind no broken system. It leaves behind a healthy one, with a limited lifetime. The planets continue orbiting because the end is not visible yet. The sun remains calm because the core still has fuel. Earth remains alive because the balance still holds. All of it is temporary. The transformation begins quietly enough to hide inside ordinary sunlight. Across deep time, that light becomes stronger. The living planet becomes empty, and the solar system moves toward an age that no human-built instrument was designed to witness. Voyager may be elsewhere in the galaxy by then, damaged, silent, and perhaps still carrying the same images beneath its record cover. The sun will not know that a fragment of its former system survives. The spacecraft will not know that the star behind its origin is changing. Their histories continue separately until the slow brightening finally gives way to something far more visible. And long after Earth has ceased to resemble the world Voyager remembers, the sun will begin expanding into a red giant. The change will not happen as a sudden explosion. It will begin deep inside the star, where the supply of hydrogen in the core has finally become too small to support the balance that kept the sun stable for most of its life. The core will contract under gravity, becoming hotter and denser, while hydrogen continues burning in a shell around it. The outer layers will respond by expanding. The sun will grow larger, cooler at the surface, and far more luminous. From a distant planet, the star would no longer look like the calm yellow disk seen from Earth today. Its surface would appear redder and less sharply defined, while the total amount of energy pouring into space would increase enormously. The familiar sun would become a different kind of star. This transformation will unfold over hundreds of millions of years. There will be no single day when the solar system wakes beneath a red giant. The star will expand through stages, changing the orbits, temperatures, and environments of every surviving world around it. Mercury will be the first major planet placed in danger. As the sun's outer atmosphere extends outward, the small inner world may be swallowed completely. Its surface will already have been heated far beyond its present state, but engulfment would erase even the shape of the planet as it is drawn into the star's extended layers. Venus is also expected to be lost. Its current atmosphere is already thick and hot, but the red giant sun would make those conditions seem mild. The planet may be consumed as the expanding star reaches farther into the inner solar system. Earth's fate is less certain. The sun will lose mass as it expands, and that loss weakens its gravitational pull. The surviving planets may move outward into wider orbits. In principle, Earth could drift farther from the growing star, but moving outward may not be enough. Tidal forces between Earth and the swollen sun could pull the planet inward. Drag from the star's extended outer atmosphere may also remove orbital energy. Small differences in how these effects unfold could decide whether Earth escapes the surface or is finally engulfed. The calculations do not all produce the same ending. What is clear is that the living Earth will already be gone. If the planet survives physically, it will not survive as the world shown on Voyager's record. Its oceans will have vanished long before. Its atmosphere may be thin, altered, or partly lost. Its surface will be scorched beneath a star that fills a far larger part of the sky. The word survival becomes almost meaningless. A lifeless rock can remain in orbit. The world that launched Voyager cannot. The spacecraft itself would be far beyond the reach of this expanding star. Its galactic orbit may place it hundreds or thousands of light years away by then, though no exact distance can be predicted honestly. The Sun's red giant phase would not physically warm Voyager in any meaningful way. Even a star hundreds or thousands of times more luminous becomes faint across interstellar distance. The spacecraft would remain cold. The light from the dying sun would leave the solar system and spread through the galaxy. But Voyager may never be close enough or correctly positioned to receive more than an indistinguishable glow among countless other stars. The star that created the spacecraft would be changing on a scale the spacecraft could not detect. This separation is one of the quietest parts of the story. The Sun's transformation will be enormous within its own system. Planets may be destroyed, moons heated, rings altered, and distant icy bodies awakened by stronger light. Yet elsewhere in the galaxy, the event will be only one aging star among billions. Voyager will not turn toward it. No instrument will notice, no memory on board will update. The golden record will continue carrying a diagram of a solar system that no longer exists in the same form. The changes beyond Earth will be complex. Mars may avoid engulfment, but its environment will be transformed by the brighter sun. Frozen material beneath the surface or at the poles could be heated and lost. For a brief period much earlier in the sun's evolution, warming may create conditions less hostile than Mars has today. But by the red giant stage, even Mars would face extreme heat. The planet would not become a second Earth. Any temporary improvement would pass. Farther out, the giant planets may experience something stranger. Jupiter and Saturn will remain far enough away to avoid the expanding surface, but the increased light and the sun's mass loss will change their surroundings. The planets themselves will respond to the sun's loss of mass. As material leaves the star, its gravity weakens. Orbits expand. Jupiter, Saturn, Uranus, and Neptune may move farther outward while continuing to circle the lighter remnant. Their years will become longer. The distances between them and the dying sun will increase. The solar system will loosen. This expansion will not release the planets automatically. The sun will lose a large fraction of its mass, but likely not enough to send the major outer planets away on their own. They may remain bound, yet their orbits will no longer match the system Voyager once crossed. The entire scale of the planetary system will stretch. Small bodies in the outer solar system will be even more sensitive. Comets and distant icy objects may be disturbed by the changing gravity. Some could be thrown inward. Others could escape. Passing stars and the tidal pull of the galaxy may strip away objects that were once weakly held by the sun. The Oort cloud may be reduced or scattered. Voyager passed through that region when the sun was still a stable star. By the time the red giant forms, much of the distant cloud may have been altered beyond recognition. The sun's outer atmosphere will also become unstable. Material will flow away in powerful stellar winds, carrying gas and dust far beyond the old planetary region. The star will shed mass for a long time. These winds will move through space, interacting with planets, moons, and any remaining debris. The quiet solar wind known today will be replaced by something far stronger and richer in material. The solar system will become filled with the remains of its own star. The planets that survive will orbit inside that changing environment. The Sunday may also pulse as its internal structure changes. Helium begins burning in the core under conditions far hotter than those required for hydrogen. The exact sequence includes stages of contraction, expansion, and instability. For a star like the Sun, helium burning produces carbon and oxygen in the core. This gives the star another period of relative stability, but it does not restore the solar system. The red giant may shrink somewhat during part of this process and later expand again. The final years of stellar change are not a single steady growth. They are a series of adjustments as the star uses the last nuclear fuels available to it. Each stage is brief compared with the long, calm life the Sun has already lived. The star spends billions of years quietly fusing hydrogen, then moves through its final transformations much more quickly. Even the brightest period will not last forever. The expanded star cannot continue burning helium indefinitely. The core will eventually become mostly carbon and oxygen, elements the Sun is not massive enough to fuse efficiently into heavier material. The nuclear support weakens again. The star enters another unstable phase. Its outer layers expand and contract. Pulses move through the envelope. More material is lost into space. The Sun is not massive enough to explode as a supernova. Its death will be quieter than that. There will be no single blast destroying the entire system in seconds. Instead, the star will gradually release much of its outer atmosphere. Layer after layer will drift away. From within the solar system, the process would still be enormous. Gas, once held inside the Sun, will spread across distances larger than the planetary orbits. Ultraviolet light from the hot, exposed core will illuminate this material. A glowing shell will form around the dying star. From far away, it may resemble a delicate cloud surrounding a bright center. This stage is called a planetary nebula, though it has nothing to do with planets. The name comes from early telescopes, where these glowing shells sometimes appeared round and planet-like. In reality, they are the outer layers of stars returned to space. The Sun will be giving back material that once belonged to its atmosphere. Some of those atoms may later become part of new stars, planets, or living systems. The solar system's ending becomes raw material for another beginning. The nebula will not remain bright forever. Its material will continue moving outward, becoming thinner and harder to see. The central star will no longer have the large outer layers that once made it a red giant. What remains will be extremely small compared with the Sun today, roughly the size of Earth. But with a large fraction of the Sun's original mass compressed inside it. The remnant will be intensely hot at first. It will no longer produce energy through the same sustained fusion that powered the Sun's long life. Instead, it will shine from stored heat, slowly cooling over periods far longer than the red giant phase itself. The planetary system around it will enter a new age. The surviving planets may continue orbiting this small, dense star. The inner worlds may be gone. The outer planets will move along wider, colder paths. The glowing nebula will fade. The solar system will become dark again, but it will not return to the form Voyager knew. The yellow sun will be gone. The broad family of planets will be altered. Earth may be absent, destroyed, or left as a scorched remnant. The distant cloud of comets will be scattered. The entire system will orbit a white dwarf. This is the real endpoint hidden beyond the red giant. A star does not simply grow larger until it disappears. It leaves behind a core. The Sun's final remnant will contain the history of everything that happened inside it, compressed into a body no larger than a planet. Its gravity will remain strong. Its light will fade slowly. Its future will stretch across timescales even longer than the active life of the Sun. Voyager may continue through the galaxy during all of it. The spacecraft and white dwarf will both become ancient remnants of the same system, separated by distances that cannot be known. One will be a dead star, the other a dead machine. Neither will remember the living Earth between them. Yet, the golden record may still preserve the evidence. The sounds of oceans, animals, weather, and human language will remain attached to a spacecraft moving through a galaxy that no longer contains the Sun as a living star. The message will outlast the conditions that made it possible. This is the final change begun by the red giant phase. The sun's expansion does not merely threaten the planets. It begins the process by which the central object of the solar system becomes a remnant. The light that once warmed Earth will fade into stored heat. The star that once filled the sky will become a small white point. The old system will survive only in pieces. Voyager will be one of those pieces, though it may be far beyond any connection to the others. And after the red giant releases its outer layers into space, the sun will remain as a white dwarf, while Voyager continues carrying the memory of the world that once orbited it. The white dwarf will be small enough to seem impossible after the red giant phase. A star that once extended across a large part of the inner solar system will be reduced to an object roughly the size of Earth. Much of the original mass will still remain, compressed into a volume millions of times smaller than the present sun. Its gravity will be intense. Its light will be different. The white dwarf will no longer shine because hydrogen is being steadily fused in a stable core. The long engine that powered the sun's main life will have ended. What remains will glow from heat stored during the collapse and from the energy left inside matter compressed to extraordinary density. At first, the remnant will be extremely hot. Its surface may shine with a harsh white or blue-white light, illuminating the expanding shell of gas that once formed the sun's outer layers. For a brief period on stellar timescales, the old solar system may be surrounded by a faint, planetary nebula. The glow will not last. The gas will continue expanding, becoming thinner until it blends into interstellar space. The white dwarf will remain behind, slowly cooling. No new fuel will restore it. No future expansion will return the yellow sun. The star that warmed Earth will have become a cooling remnant. The surviving planets, if they remain bound, will orbit farther away than before. The sun's mass loss will have enlarged their paths. Their years will be longer, and the light reaching them will be weaker once the bright nebula fades. Jupiter and Saturn may still exist. Uranus and Neptune may continue moving through deep cold. Their moons may remain, though changed by billions of years of impacts, radiation, and gravitational interactions. The system will be recognizable only in fragments. The central star will no longer resemble the sun Voyager knew. The inner planets may be gone. Earth may have been engulfed, destroyed, or left as a scorched body on a widened orbit. The distant comet cloud may be scattered by mass loss and passing stars. The old architecture will survive as a damaged outline. Voyager's golden record will preserve a different version. It will carry images of a bright sun over landscapes filled with water and life. It will preserve diagrams of planets arranged around a star in its stable middle age. It will hold voices spoken beneath an atmosphere that may no longer exist. The record will not change when the solar system changes. That is the nature of a message fixed in material. It preserves one moment by refusing to move with the world it describes. This difference turns the golden record into something more than a greeting. It becomes evidence of a lost arrangement of matter. The message says that there was once a living world around a star. It does not guarantee that the world still exists. It does not guarantee that the species that made the record survived long enough to watch the sun change. It only proves that at one point, someone was here. Voyager itself may also have changed beyond recognition. The spacecraft was never designed to survive the age of the sun. Its materials may endure for an extraordinary time in the emptiness between stars. But billions of years expose even a small object to risks that cannot be ignored. Dust grains may strike the surface. Radiation may alter the structure of materials. Temperature changes during close stellar passages may weaken components. A rare collision with a larger particle could damage or destroy part of the probe. The chance in any single year is extremely small. The timescale is enormous. Voyager may remain largely intact, carrying its dish antenna, booms, instruments, and golden record through the galaxy. Or it may be reduced to several pieces following slightly different paths. The golden record could remain attached. It could be scarred. Its cover could be punctured. Its surface could lose some of the information engraved into it. There is no honest way to know which future occurs. The spacecraft's survival is not promised by space. Emptiness only makes long survival possible. If the record remains readable, it may outlast every active technology that has ever existed on Earth. It requires no electrical power to preserve its information. It does not need a computer, receiver, or antenna. The information exists physically in the shape of the grooves and in the engraved instructions on the cover. A future intelligence could still solve the puzzle. Engineering leaves patterns that natural objects rarely contain. A smooth metal disc, engraved diagrams, and carefully arranged components would show intention. The hydrogen symbol might reveal the scale. The pulsars might provide a route backward through galactic history. The finder would be looking at archaeology across time rather than distance alone. It might discover not where Earth is, but where Earth was. That distinction becomes important after the Sun's death. If Earth is gone, following the record's map does not lead to a living civilization. It leads to a white dwarf and whatever remains of its planets. The finder may arrive to see no oceans, no cities, no radio signals, no obvious source for the voices stored on the disk. The record could become the only surviving evidence that the system once supported complex life. A machine found somewhere else in the galaxy would describe a dead star as the origin of a living world. The contradiction would be real. The star died after the message left. Voyager would become a messenger from a system that no longer resembles its own description. This possibility gives the white dwarf sun a strange connection to the silent spacecraft. Both are remnants. The white dwarf is the remaining core of a star. Voyager is the remaining artifact of a civilization's early space age. Each carries a compressed history. The star contains carbon and oxygen, produced through billions of years of fusion. The spacecraft contains images, sounds, and materials assembled during a few decades on Earth. One remnant was created by gravity and nuclear physics, the other by memory and intention. They may continue for timescales longer than the living systems that made them possible. The white dwarf will cool very slowly. At first, it will still be bright enough to illuminate its surviving planets. Over billions and then trillions of years, the stored heat will escape into space. The remnant will become dimmer. Its color will shift. The old solar system will receive less light. Eventually, the white dwarf will approach the temperature of the surrounding universe. A fully cooled remnant is sometimes called a black dwarf, although the universe is not yet old enough for any black dwarf to exist. The cooling process takes far longer than the current age of the cosmos. This means the sun's death is not the end of its physical presence. The remnant may continue long after galaxies have changed and many stars have gone dark. Voyager could also continue, if chance allows it. The spacecraft and the white dwarf may both remain in the galaxy as cold objects, separated by an unknown distance. Their common origin would not be visible through motion alone. The white dwarf stays with the altered planetary system. Voyager follows its own galactic orbit. One remains near the place that was once home. The other carries home away. Their paths may never cross again. The scale of loss is difficult to measure because the process is so slow. From 1 million years to the next, the white dwarf changes only slightly. Voyager travels a little farther along its galactic path. The golden record accumulates another small amount of damage. Nothing appears dramatic. Across billions of years, almost everything becomes different. The same quiet pace that allowed the sun to shine steadily also allows its ending to fade into an almost endless future. The spacecraft may pass near other stars during this time. A close encounter could change its path. heat one side slightly, or expose it to a denser region of dust. Most encounters will still be distant. Voyager is too small and the galaxy too empty for discovery to be likely. The record may remain unread for the entire lifetime of the white dwarf. It could preserve Earth perfectly enough to be understood and still never be found. A message does not require a recipient to exist. It only requires someone to have sent it. This may be the deepest purpose of the Golden Record. It was not a realistic attempt to begin a conversation with a known civilization. It was a statement that a small world had become capable of imagining a future beyond itself. The record was attached to Voyager, even though the chance of discovery was almost zero. Its creators knew the spacecraft would travel for far longer than they could follow it. They chose to send evidence anyway. By the time the sun becomes a white dwarf, that choice may be one of the few recognizable human decisions still moving through space. The spacecraft's other systems will no longer express intention. A dead computer looks like material. A silent antenna points nowhere. Scientific instruments become unfamiliar mechanical structures. The record remains visibly designed to be interpreted. It is the part of Voyager that still asks to be understood. The request may outlast the language of the people who made it. It may outlast humanity. It may outlast Earth. It may outlast the bright sun. Yet even if the disk survives, it cannot preserve the experience of being alive on the planet. It offers sounds and images, but not weather on skin, gravity beneath a body, or the full meaning of a human voice. A representation is not the world. The record is small, because every archive is small, compared with what it tries to save. Earth contained billions of lives, changing ecosystems, cities, oceans, histories, and thoughts that never entered the selection. Voyager carries only a few fragments. Those fragments become more powerful as the source disappears, but they do not become complete. A finder might believe the images represent the most important things about Earth. They were only examples. The world was larger than the message. This incompleteness makes Voyager more human, not less. The record does not claim to contain everything. It sends what could be carried by one small machine, leaving the solar system in 1977. The limitations are part of the artifact. The technology, design, and choices reveal the error as clearly as the images themselves. A civilization reading the record would learn that humans had reached the outer planets, but had not yet mastered interstellar travel. Voyager was fast enough to leave the sun. It was far too slow to choose another star. The record belonged to a species standing between worlds, capable of sending a message into deep time, but unable to know whether it would ever be received. When the sun dies, this condition will not have changed for Voyager. The spacecraft will still be on an unplanned path. Its exact location will depend on every gravitational encounter and uncertainty accumulated across billions of years. The record may still exist, but it will not tell us where the probe is. It tells us where the journey began. That difference returns us to the question at the center of the video. Where will Voyager be when the sun dies? The white dwarf can be described. The altered solar system can be imagined. The golden record can be followed in principle. But the spacecraft's true position is hidden by time. We can say that it will likely remain somewhere within the galaxy, moving on an orbit shaped by events no present map can contain. We can say that it may be hundreds, thousands, or far more light years from the sun. We can say that it may have survived, broken apart, or been captured by a chance encounter. None of these possibilities provides one final location. The record gives the future a memory. It does not give us certainty. The last part of Voyager's story therefore cannot be a precise map. It must be an honest journey into what can still be known after billions of years. The sun will have become a white dwarf. The Earth of the record will be gone or transformed. Voyager may continue carrying its message. But where the spacecraft itself will be is a question whose answer lies beyond any path we can calculate today. And with the sun reduced to a fading white dwarf and the golden record still traveling through the dark, the final question is no longer what Voyager carries, but where the galaxy may have carried Voyager itself. There is no single point we can place on a future map. For the next tens of thousands of years, Voyager's path can still be described with some confidence. Its speed is known. Its direction has been measured. Nearby stellar motions can be projected far enough to reveal encounters such as the distant passage near Gliese 445. But the death of the Sun belongs to a very different timescale. Billions of years separate Voyager's final signal from the white dwarf that will remain at the center of the altered solar system. Across that span, the spacecraft will pass through a galaxy that never stops moving. Stars will approach and recede. Clouds of gas will drift through the disk. Gravitational encounters will add tiny changes to the route. A change too small to matter across a century can become enormous across an age. This is why Voyager's exact future position is unknown. It is beyond the precision of any map we can build today. The spacecraft will have a real location when the Sun dies. It will occupy one narrow point in space, moving at one particular speed through one particular region of the galaxy. Physics will not become uncertain for Voyager. Our knowledge will. The present measurements contain limits, and those limits expand with time. A slight uncertainty in the position of a passing star can alter the predicted distance of an encounter. That encounter may change Voyager's direction. The new direction then affects every later passage. The path becomes a history that has not happened yet. We can describe the forces. We cannot list every future event. This does not leave us with nothing. Some broad possibilities remain, far more likely than others. Voyager will probably still be gravitationally connected to the galaxy rather than escaping into intergalactic space. Its velocity is enough to leave the Sun, but not enough to leave the Milky Way on its own. The spacecraft should continue following a long galactic orbit. It may travel above or below the broad disk before gravity draws it back. It may cross regions with different densities of stars. It may pass through a quiet stellar neighborhood or move near a cluster that does not exist today. The exact scene is hidden. The general journey is not. Voyager will almost certainly be far from the white dwarf Sun. It may be hundreds of light years away. It may be thousands. A sequence of gravitational encounters could place it farther still or bring its galactic path through a region closer to the Sun's own orbit. Yet even if the two objects occupy the same broad neighborhood again, they are unlikely to meet. The galaxy does not return objects to their beginnings. Two paths can cross the same region millions of years apart. They can pass through nearby space with completely different velocities. They can orbit the same galactic center and remain separated forever. Voyager will not complete a circle around the Milky Way and arrive back at Earth's old address. There is no fixed address left to reach. The Sun will have moved through many galactic orbits. The planets will have followed it. The entire local neighborhood will have changed. Home will be a path, not a place. Voyager's path will be another. This makes the title's question both answerable and impossible. Where will Voyager 1 be when the Sun dies? It will be somewhere in the evolving galaxy, carried by the motion it inherited from the solar system and reshaped by whatever it encounters along the way. That is the honest answer. Anything more precise would pretend that billions of years can be reduced to a straight line. Voyager itself may no longer resemble the spacecraft seen in photographs. Its body could survive largely intact, protected by the emptiness between stars. The dish antenna may remain attached. The booms may still extend from the central structure. The golden record may remain beneath its cover. Or time may have altered it. A small impact could break a thin structure. Radiation could weaken materials. A rare collision could tear the spacecraft apart. If that happens, Voyager would not vanish entirely. Its fragments would continue moving through the galaxy, each carrying part of the original velocity. The object called Voyager 1 might become a small group of human-made debris spread across space. The journey would continue without the original shape. Perhaps the golden record would remain with the central body. Perhaps it would separate and follow its own path. The message could outlive the machine that carried it. Or the machine could outlive the readable message. Both futures are possible because preservation and meaning are not the same thing. A metal disc can remain physically present after its surface has been damaged beyond interpretation. A spacecraft can remain recognizable after every trace of electrical function has disappeared. Deep time removes purpose before it removes matter. Voyager was built to explore Jupiter, Saturn, and the edge of the Sun's influence. Every instrument had a function. Every command was connected to a mission. Billions of years later, function will be gone. Only form may remain. There is no reason to expect Voyager will ever be discovered. The chance remains extraordinarily small. The galaxy contains an immense number of stars, but Voyager is tiny and does not travel toward a known inhabited system. It may pass through billions of years without coming close to anyone. The golden record could remain unopened forever. Its existence would still matter. A message does not become meaningless because no one receives it. It records the moment when its makers became aware of the scale beyond their own lives and chose to speak into it anyway. The record says that humanity understood something important. The spacecraft would outlast the mission. The journey would outlast the people who launched it. The universe would continue whether the message was heard or not. That understanding is built into Voyager's design. From the perspective of the galaxy, the spacecraft is almost nothing. It has no significant mass. It does not alter stellar orbits or reshape clouds. Its passage is too small to leave a visible mark. From the perspective of Earth, it carries something enormous. It carries proof that a species once looked beyond its own planet and built an object for a future it could never enter. This difference in scale has followed Voyager from the beginning. The spacecraft is physically small, but the distances attached to it are vast. Its transmitter is weak, yet its signal crossed the solar system. Its computers are primitive by modern standards, yet they guided a mission farther than any earlier machine. Its golden record contains only a tiny selection from Earth, yet it may become the longest-lasting version of Earth ever created. Voyager's importance is not measured by size. It is measured by duration. The duration ahead may be far greater than the time behind. By the time the Sun becomes a white dwarf, Voyager's active mission will occupy an almost invisible fraction of its history. The decades of communication, planetary images, engineering problems, and recoveries will be compressed near the beginning. Nearly everything else will be silence. The spacecraft will spend ages crossing distances without reporting them. It may pass near stars whose names were never known on Earth. It may enter regions that no telescope has yet studied. It may survive changes in the galaxy that cannot be pictured clearly today. No one will watch from its point of view. There will be no final image of the red giant sun, no measurement of the white dwarf, no photograph showing the galaxy around it. Voyager will be present in the future without becoming a witness to it. This is an important difference. A witness remembers. Voyager only remains. Human beings give the spacecraft a personality because its journey resembles something alive. We say it explores, speaks, leaves home, and travels alone. These words help us understand the story, but the spacecraft experiences none of them. It does not feel the sun fading behind it. It will not know when the star dies. It will not recognize another star as closer. It will not wait to be found. The loneliness exists in our interpretation. The motion itself is silent and neutral, yet that interpretation is not false. Voyager is human because humans made it, chose its route, listened to its signal, and attached meaning to what it carries. Its journey becomes a way to understand our own place in time. We live during the brief period when the sun is stable, Earth is alive, the oceans are full, and Voyager can still be remembered by people close to its launch. None of these conditions is permanent. That does not make them insignificant. It makes them rare. The video began by following a machine farther into the future than any mission was designed to survive. At first, that future was measured in years, the declining power, the final instrument, the last signal. Then the scale widened. Centuries carried Voyager toward the Oort cloud. Tens of thousands of years brought it near another star. Millions erased the familiar sky. Billions separated the spacecraft from the solar system's living age. At the end of that widening story, Voyager has not reached a final destination. It has become part of the galaxy. The spacecraft's true future is not one encounter, one star, or one coordinate. It is continued motion through a changing gravitational system. The sun's story has a more visible ending. It grows brighter. Earth becomes uninhabitable. The star expands. Its outer layers leave. A white dwarf remains. Voyager's story does not end in the same way. There is no planned transformation. No final orbit, no destination that completes the mission. The spacecraft simply becomes older. It may be destroyed by chance. It may be captured by a star. It may continue freely for longer than the current age of the universe. All of these futures begin with the same small object already moving away from us tonight. This is why the answer cannot be a location. The real answer is a condition. When the sun dies, Voyager will no longer belong to the active history of the solar system. It will be an ancient object moving through a galaxy that has carried it far beyond every map, signal, and prediction created at launch. It may still carry Earth, but it will no longer carry a route back to Earth. The pulsar map describes an origin. The images describe a moment. The sounds describe a living world. None of them can keep that world alive. The record does not defeat time. It only allows one small part of the past to travel with it. Perhaps this is what makes Voyager's future feel both peaceful and unsettling. The spacecraft does not struggle against the distance. It does not fear the loss of the sun. It does not need the solar system to remain unchanged. It continues because motion continues. The fear belongs to us, because we understand what will be lost. The calm belongs to the universe, because nothing in that loss violates its rules. Stars age, planets change, machines fail, orbits continue. A message can travel long after the voice behind it is gone. Somewhere in the far future, the white dwarf Sunday may shine faintly over the remains of its planetary system. Earth may be absent or present only as a lifeless fragment. The oceans, cities, and people recorded by Voyager will belong to a past older than almost anything we can imagine. And somewhere else, in a location no calculation can identify today, Voyager may still be moving. Its surface may be scarred. Its antenna may point nowhere. Its systems may be silent. Beneath a damaged cover, the golden record may still hold a few sounds from Earth. Not because the spacecraft saved the planet. Not because it escaped the death of everything. But because, for one brief moment, a living world sent part of itself beyond the future it could survive. That is where Voyager will be when the sun dies. Not at one destination we can name, but somewhere inside the moving galaxy, carrying an ancient memory farther than anyone who made it could ever follow. Thank you for watching this calm journey into Voyager 1's distant future. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys through the mysteries of the universe, and tell me whether you think Voyager's golden record will ever be found. I will pin the most thoughtful answer. Tonight, you were watching the Just About Space channel, talking about where Voyager 1 will be when the sun dies. Sleep well, and keep looking up. Good night.